It's Tom Kennedy Science, and I'm Dr. Tom Kennedy. Now, today, we're going to start a series of lectures. I know, I'm always starting series of lectures, but this time, we're going to talk about the history of the Earth and life on it. So, this is one of my favorite topics to think about, starting with the origin of life to the modern diversity that we see today. Now, of course, this is a phylogenetic tree representing all the major branches of life. So if you think about it, you go almost anywhere on this planet and there's life at the bottom of the ocean, the top of the mountains, floating high in the atmosphere, even down in the rocks right below you. This world is teeming with life. I mean, think about all the different types of insects and fish and birds and flowers and animals or plants you have never even seen before. This planet, like I said, is unique. It is just teeming with life. So the question becomes, how did we go from a planet without life to what we see today, just covered in all different types of life forms? So as I go through the history of the planet, think about this. What are the key evolutionary innovations that led to the world and the diversity we see today? And another key thing to think about, the Earth and life are connected to each other. And in fact, one of my favorite ways of thinking about life is that we are an extension of geological processes. So the Earth geology affects us, and guess what? Life affects the Earth and the climate as well. So let's start this, right? I get excited thinking about this kind of stuff. So what I want to begin with is go all the way back to the origins of the Earth. And I want to do a brief explanation of how we know how old the Earth is, because it's pretty old. And then I'm going to go through the different geological ages of the planet, and I'm going to discuss what's happening during each of those ages and kind of emphasize some of these key or major evolutionary innovations that are occurring. Here we go. We're going to move through time. We're going to cover the Hadean, the Archean, the Proterozoic will be the Phanerozoic eon, where I will break that down into the Paleozoic, the Mesozoic, and the Cenozoic eras. All right, so keep in mind, what are these important evolutionary innovations that are taking place throughout geological time? Now, one of the reasons why this world is covered in life, lots of reasons why, the Earth is kind of old. It's a middle-aged planet. It's 4.6 billion years. And this pie chart on the right of me, it kind of shows you the different geological eons, okay? And if you notice, the Archean and the Proterozoic are the longest eons. And the eon we're in right now, the Phanerozoic, which means basically visible life, is only 12% of the Earth's history. That's it. Most life that we are familiar with, animals and plants, have only been around for 12% of the Earth's history. So the Earth is really old. And you see that little pie get smaller and smaller and smaller. That Cenozoic, the last 65 million years, yeah, that's been the rise of mammals. So what are these eons and eras and periods and epochs I talk about? Well, because the Earth is so old and a lot has happened, we divide its history into eons, eras, periods, and epochs. Now, eons, of course, are the longest one, and they last hundreds of millions of years to the Proterozoic that was like 2 billion years long. And then the shortest one would be the epochs. So we are now in the Holocene epoch, okay? That would be the latest one. And these last maybe a few million years. We've been in the Holocene for only 11,000 years. And the previous epoch before the Holocene was the Pleistocene, and it lasted about 2.5 million years. Now, our current time, what are we in? Of course, we're in the Phanerozoic eon, We are in the Cenozoic era that began 65 million years ago. We are in the Quaternary time, and our epoch is the Holocene. And as you notice, the Holocene is only the last 11,000 years, and that encompasses all of our civilization. Now the question is, whenever we find fossils, rock layers, how do we know how old they are? How do we know how old a mountain is? How do we know how old a rock is? Or, for that matter, the Earth itself? We use something called radiometric dating. Now, most people say we use carbon-14. Well, we only use carbon-14 for things that are about 50,000 years old or less. But we use radioisotopes of other elements, like uranium. Uranium has a half-life of over 4 billion years, and it will slowly decay into lead through a series of reactions, right? It's kind of complicated. But we know with these radioisotopes, these are isotopes of elements that are unstable, so they decay into other elements called the daughter isotopes. And they do this at a set time that's not affected by temperature, not affected by pressure, not affected by chemistry. So I can look at my ratio of my parent to daughter isotopes, and I can age the rock or the fossil or the rock layer. And what's nice is we don't rely on just one isotope. We might use several isotopes. And when all these isotopes give us a similar age, we know we're doing it right.